Great. Thank you very much for inviting me to talk today. I'm going to carry on thinking about how we can investigate changes in intermediate water masses between glacial and interglacial conditions. And I'll set the scene just by showing this cartoon, just to illustrate that we have two very different ocean configuration states between the interglacial and the glacial condition. So here's today to illustrate the interglacial condition. We have strong deep water formation in the North Atlantic, and as this flows south, it becomes modified and mixes with surrounding waters and upwells in the Southern Ocean as circumpolar deep water. Some of this will flow south to form Antarctic bottom water. Some of it will flow north, where it will become mixed in deep water convection processes to form these intermediate water masses flowing out here. We know we interpret from benthic foraminiferal stable isotope data that the last glacial maximum was a very different place to be, that we had a very much more expanded Antarctic bottom water in the North Atlantic, and also that the North Atlantic deep water was actually shoaled, and it was more of an intermediate depth water mass. And as the previous speaker said, we know much less about what was going on in the Antarctic intermediate waters at this time. So what happened as we flicked from one state to another? I'm very much interested in this, in particular from the point of view of the silicon cycle. So if we take a look at a sort of nutrient-like nitrate or phosphate in this case, we can see that the ocean configuration today leaves us with a very strong north-south divide with very nutrient-poor North Atlantic deep water as a result of very near-complete utilization of nutrients near the surface in the north, as opposed to nutrient-rich southern source waters. And that's because we have very much more incomplete nutrient utilization in the Southern Ocean, resulting in high preformed nutrients. And we think that this is because we're having limitation of the productivity in the Southern Ocean, most likely as a result of low micronutrients such as iron. The situation is slightly different for the silicon cycle. So this is a map, again, going from south to north, of the silicic acid concentration in seawater. So silicic acid is a key nutrient for organisms that make biogenic opal, such as diatoms. Diatoms are algae that are responsible for nearly half of the marine export of carbon. And they grow predominantly in the Southern Ocean. So as you have this North Atlantic deep water upwelling in circumpolar deep water, some of that will flow south. That will go and be used up by diatoms, but as the diatoms die and sink, 97% of their opal gets dissolved back into Antarctic bottom water. However, the stuff flowing north that forms the intermediate water and subantarctic mode waters, because of this deep remineralization and this very high diatom productivity, those waters will be very low in silicon with respect to other nutrients such as phosphate. And these waters are important. They go into influencing the thermocline in a large portion of the global oceans. So one idea that was put forward about 15 years ago now, that during the glacial you could actually have, as a result of high iron input to the Southern Ocean, a change in this system such that these waters exported much higher silicon to other nutrient ratios. So did this happen? And what would the influence be of switching between these two different states? So I did the study now a few years ago to start investigating this idea of silicic acid leakage through Antarctic intermediate waters. And I used some sediments from a core about 1,000 meters off the coast of South America. And the proxy I used was silicon isotopes and sponge spicules. And I don't really have any time to go into this today, but essentially these isotopes record the ambient silicic acid concentration where the sponges grow, and they're benthic, so they go on the sea floor. I will, for the sake of time, just go through some of these records here. This is going from 0 to 30,000 years ago. And just to give you some context, up here in red we have the Greenland ice core oxygen isotope record, and in black the prototinium thorium record from Bermuda Rise. And highlighted are Younger Dryas and the Heinrich Stadials in blue. This record here is a diatom accumulation record from the northwest coast of Africa. I'll come back to that later. And here, focus on here for a minute. These records are those spicule silicon isotopes. The hollow symbols are from the deep Southern Ocean down here, and these black symbols are from the 1,000-meter site here. And what is obvious, hopefully, to start with, is that there's no difference between the LGM, roughly here, and today in terms of silicic acid leakage. So we don't really seem to be seeing this leakage happening. But what we do see is that during these abrupt events, we are getting spikes of silicic acid coming out into the Antarctic intermediate water, which we interpreted as indicating that there was a sort of better ventilation of Antarctic intermediate water at this site during these times. So if we go back to those diatom records just for a minute, so here are some really nice records that were published last year by Meckler and co-workers. Up here in the blue-green records are actually Bob Anderson's data from here in the Southern Ocean, showing opal flux. This is from 0 to 20,000 years ago this time. And these oranges and reds and these purple records here are from these cores up off the northwest coast of Africa. And what we can see is that in both of these locations, you're getting spikes of opal flux during the Heinrich Stadial One and the Younger Dryas. So the question is, what drove this increase in diatom productivity at the time? This was one of the ideas that was put forward in this paper, was that it was actually a result of large oceanographic changes. So here's today, sorry, it's flipped, so now here's the north and here's the south. So you have the strong overturning in the north. Here's the Antarctic bottom water with lots of silicic acid in it. At the LGM, we have that shoaled boundary between the north and the south water, and this boundary shoaled even further during the Heinrich Stadials, allowing some of that silicic acid to diffuse into sort of thermocline depths. There's also a possibility that we had changes in the Antarctic intermediate water getting into the North Atlantic at this time, but as the previous speaker introduced very nicely, there is some very conflicting evidence about this. There's evidence that there's actually much weaker Antarctic intermediate water flowing into the North Atlantic at this time. I think key to this question is really going to be understanding the strength of the North Atlantic overturning at this time. Was it weaker or was it just shallower? Alternatively, though, there's a third possibility, which is that actually all of these records are reflecting much more localized or regional processes, and that they sort of happen at the same time because we're having connections via atmospheric links. So these local processes could be changes in coastal upwelling, wind-driven upwelling, frontal zones, and so on. So I'm going to talk for the rest of this talk about this. I'm going to address this question here, which is, what was the nature of the intermediate depth water in the North Atlantic during the deglaciation, very much from a point of view of the silicon cycle. And just in case any of you need to leave or I've run out of time, this is the sort of punchline. I'll be showing you some silicon isotope records from off the southeast coast of Iceland, again using spicules. And these two cores are 2,100 and 1,200 meters, and they very much suggest that it's the same water mass at those two depths. They show that there are some fluctuations in silicic acid concentration, but they're very moderate. They really don't seem to be reflecting a very high proportion of Southern Ocean water, not very high proportions of Antarctic bottom water, and not really any indication of this sort of enriched silicic acid-enriched Antarctic intermediate water either. So I'm going to sort of then show a little bit of a few diatom assemblage data to suggest that perhaps these diatom blooms are actually a result of more localized processes in this area. Okay, so this is the first North Atlantic spicule record that was published earlier this year. This is from a site at about 1,400 meters off the coast of off the Carolina coast here. And here are the same records, just to give you some context again. Here's the ice core record from Greenland, ferritium thorium record from Bermuda. This is just the core oxygen isotopes here. But I want you to focus on these purple symbols here. This is the silicon isotope value of the spicules, translated, as it were, into silicic acid concentrations, going from 0 to 20,000 years. And you can see that during the glacial, these values were marginally higher. There's a sort of tentative higher value during Heinrich Stadial. This core site today, I should say, is today in the deep western boundary current, but there is some sedimentological evidence that this deep western boundary current may have changed in the glacial. But essentially, what should also jump out of you here is that this is a really low resolution record, and I was very much restricted here by the sedimentation rate during the glacial and deglacial. So what I really wanted was to get some nice high resolution records. So I turned to a couple of cores off the coast of Iceland here. So this is a transect here going from A to B along that line. And these two cores are situated at just over 1,000, just over 2,000 meters here. And this is just plotted against modern day silicic acid concentration here. And these are beautiful high resolution cores. So I'm just going to show the data fairly quickly, so apologies for rushing through this quite rapidly. They're both going to be in the same format. So in the purple at the top, we have the percentage of Pachyderma sinistral, just to give an idea of surface or thermocline temperatures. So this is plotted so that we have warm and cold, so warm up the page. We have ice volume corrected, benthic oxygen isotopes and benthic carbon isotopes from David Thornalley. And here in the red symbols are the sponge silicon isotopes, and these are plotted so that silicic acid increases up the screen again. And down here, this is just the spicule morphology data. This is essentially just to show there's no bias from the different morphologies. So this is the shallower core, and again, sorry for rushing through this quickly, but here's the deeper core. Again, this is the same things plotted, but this is a slightly expanded section from 8 to 18,000 years this time. And just to make things a bit simpler, essentially what I'll just try and convince you quickly is that these two cores very much reflect the same magnitude of changes in silicic acid. So to make things simpler, I've essentially just plotted those two together, assuming that they're the same water mass. And you get something like this. So this is again going, this is 0 to 18,000 years with a bit of a gap there. Up here we've just got some records just to illustrate what was going on in terms of ocean circulation at the time. These are two nearby cores. This is Ian Hall's Protictinium thorium data and some Pretorius's sortable silt data from ODP 984. And here's the benthic carbon and the benthic silicon again. And what I've done is for every depth where I had silicon isotope data, I've taken the benthic carbon data as well. So these are from exactly co-located depths in the same core. And what I've done here is, in this bottom panel, is essentially just add them together. And all I've done there is to pick out as strongly as I can the nutrient-like signals in these records. So first thing is to think about these sort of magnitude of changes here. What we see here is that if you take it, as for face value, as it were, and translate these directly onto silicic acid concentrations, you actually get a sort of value ranging a change of about 20 micromolar. But this is probably going to be exaggerated by changes in the silicon isotope composition of seawater. So it's more likely to be only about a 10 micromolar change, which is not a very big increase. It's a very moderate increase. So it's unlikely to be influenced heavily by Southern Ocean water. What we do see is that this very strong nutrient signal comes out here at just shy of 15,000 years ago, and this seems to coincide with changes in the sortable silt record nearby as well. So we think it might well be something to do with relatively local changes in the strength of the overflow, switching between very silica-poor Arctic and slightly more enriched silicon waters from the south. So just before I finish, I just thought I'd show you also some quite neat diatom assemblage records from the same core. Well, this is actually from 154P. This is work I've been doing with Jenny Pike in Cardiff and our master's student, Jordan Eastwood, who is very patiently counting lots of diatoms. And there are some really neat signals that come out here, and I don't have time to go through them all. But what I will pick out is just one species, which is this guy here. This is Coscinodiscus oculus iridis, a very beautiful, large, centric diatom. And I mean large, this is like something you can actually pick them out like a grain of sand. And this is actually this record here, excuse my shaking hand. And what you can see is that these peaks in oculus iridis actually coincide with increases in the coarse fraction. And we know from the modern, there's been ecological studies done of these guys, that they really like sort of cold, low salinity Arctic waters. So this sort of just sort of feeds in quite nicely the idea that these diatom blooms are actually being caused by more likely sort of iceberg activity, iceberg melting, or perhaps even frontal movements, bringing more Arctic waters into the site during these times. So I think with 1 minute left, I will go back to the summary slide just to say that I was hopefully convincing you that we can use silicon isotopes to address this question of the nature of the intermediate depth water during the deglaciation, and that we have evidence from the high latitude North Atlantic now that down to a depth of more than 2,000 meters, we're not really seeing a very strong Southern Ocean signal there. I'll stop there. Thank you.